evening. Hi, everyone. Welcome. Welcome to CCA. Hello, live stream people. It's good to see you as a little blue light in the upper ceiling area there. My name's Sarah Fox. I'm the host and curator of Sense of Place, and this is our 15th season. Tonight, we are here to have Dick Iverson talk to us about Geology Alive, understanding the geologic. Oh, hold on, this isn't right. Hold on one sec. Let me just check. It's not you guys, it's me. I'm sorry. This just doesn't feel quite. Wait. There we go. Okay. All right. I knew something was not right. Thank you. All right. Let's try this again. Tonight we're here to see Geology Alive, understanding the geologic hazards in the Gorge, of which we have a lot, with Dick Iverson, who you're going to hear more about in a second. We have a lot of people here tonight, a ton of people online, as Cole said. I'm not going to do this every time, but we sold out so early, and there was enough sad emails that thanks to Interfluve, I was able to arrange to do this again. But don't expect it, okay? All of our shows are online now. You can buy tickets to all of them now. Do it, because I don't like sad emails. Here's how it's going to work tonight. I am going to do some more introduction. We're going to follow that with a Q&A with Dick. I think that's sometimes when the best stuff comes out. Don't be scared to ask the question that you think is stupid, because I ask a lot of them, and the people are always nice. So if those pop up along the way tonight, be ready to ask. I also want to tell you about MAI. As some of you guys may know, Sense of Place is a program of Mount Adams Institute, which is a local nonprofit doing work on a national level to help people from all different walks of life connect to the natural world and really support some of our agencies like the Forest Service or USGS in fulfilling their job to serve the public and take care of our natural places. So thank you to MAI. They're a great program to be a part of. And thank you to our sponsors. Many are here tonight. I also want to thank many of you guys, and I noticed especially this time, many of the folks at home. The live stream is something it's really important to me, because I want our shows to be as accessible to as many people as possible, both here and elsewhere. And we offer it for free, but I noticed how many of you guys took the time and were able to donate a little something, even though you're tuning in from home. And I want to say thanks, because with a program this size, those little bits make a difference. So when I was a sophomore in high school, I got to go abroad for the very first time. And I was on a basketball team, and we got to go to Japan, which was a really big deal to me. I was a little farm kid, so. And we went to Japan, and the second week of the trip we each got to go stay with a homestay family, which was really great, except one night we had octopus, and I was not a courageous eater, so that was scary. But the first week, we stayed in a hotel unlike any that I'd ever seen. Instead of being, sort of a sprawling hotel where you walk down a long hallway and there's room after room after room, this hotel was very columnar, and there was maybe like 4 or 5 rooms per floor. So one day, the whole basketball team was in my room, and I think I was on the 23rd floor. And we were sitting on the floor just playing cards and waiting, for the bus to come so we could go to our game. And the curtain was moving, and one of the captains was like, it's too cold in here. Someone go close the window, you could tell the window was open because the curtain was moving. So, probably one of the freshmen got up and went over to close the window and got to the window and realized this window's not open. And as soon as she was standing, she realized that the reason the curtain was moving is because the whole building was moving. And the whole building was moving because there was an earthquake happening. And so being the good Pacific Northwest kids that we were, we knew, don't go get in the elevator, go down the stairs and get out. So if you can imagine this group of 12, sort of a motley crew of a basketball team, we yelped and gathered ourselves up and went out and found the staircase and started running down 23 flights of stairs, sure that like death was imminent. And we're running and we're running and we're in good shape, but we're still getting tired and it's really scary because the building is moving and we're on the 23rd floor and what's happening, and some people are in better shape and some people are in less good shape, and we get all the way down to the bottom and it is this weird room. It's not the lobby, and there's like a half door and we don't know where to go, and we open this weird half door and down even below it is this room full of Japanese people working on computers who look at us like, what the hell are you guys doing? And it was super surreal and scary because it was like, you're in this subterranean zone on computers, what are you doing? And we were scared and they were scared, and so we closed that door and figured, well, we must have gone too far, and so then we ran back up one more floor and opened the door, and we were in the lobby, thank God, and no one is running around, and we're thinking, we're about to save everyone's life here because clearly no one understands what's going on. And so this team, and we had 2 girls who were 6 foot, I mean, we were not hard to miss. We all run out, and we look at the people who behind the counter at the lobby, and they are just cool as cucumbers. And we're trying to tell them in English, there's an earthquake going on, you guys. And they looked at us, and they didn't understand what we were saying entirely, but they knew earthquake, and they knew enough to let us know that it was not a big deal. And we tried to convince them, and they let us know it was not a big deal. And they're the locals, so we trusted them. We took the elevator back up to the 23rd floor and carried on. But I never forgot that story. And a few years ago, OPB did a special on earthquakes. And as part of that special, they went to Japan. And I discovered that in Japan and other places, there are people building skyscrapers that are actually made to move. And I'll tell you, Google it when you get home. Google Japanese swaying skyscraper, earthquake. And you will see an urban skyline with, skyscrapers, and then you will see huge buildings just going. I mean, I was talking with Dick, they even have some buildings on rollers that just roll. It is the weirdest thing to be Googling something with earthquake in the name, and instead of it coming up with videos of carnage, it is the most serene, peaceful thing. So a very different story happened in 2014. This is when I really fell in love with geology. I was hired to produce a short video on a local geologist, Scott Burns, Sense of Place alum, was also an Oregon Scientist of the Year, great storyteller. Scott's the one who told me, road cuts are God's gift to geologists. And I've never forgotten that. I don't know what it means when I drive through, but I know it's important to them. So I was doing this story on Scott, and as part of that story, he said, you should go talk to this gal who had tried many years ago to prevent an apartment complex from going into some natural area near her house that she wanted to preserve. And so I go and talk to her, and the story was, there was this natural area park near where she lived, and the city was planning to develop it with apartment buildings. And she didn't want that. And so folks said, go talk to Scott Burns, and maybe he can help you figure out some more information about that location and help you out. And so she went and talked to Scott Burns and said, here's what I'm trying to do. They want to develop it. I don't want them to develop it. Can you go just take a look around? Let me know what you see. And Scott's, yeah, I'll take my grad students out. We'll go see what's out there. So Scott goes out with his grad students, and they survey the land, and they very quickly realize that where they want to build the apartments is the location of an ancient landslide. And it's very clear. It's hummocky topography, I think he called it. So he comes back, and they have all the research, and they have all the data, and they say, this is a very high-risk area. It's an ancient landslide. You absolutely should not build here. What do you think they did? they built there. And a few years later, guess what happened? Yeah. So if anyone knows Northwest News, I went and talked to Bruce Sussman, who was a news reporter, who did the story on the local evening news that showed the buildings evacuated sliding down the hill from a helicopter. And so the grad students in Scott were right. You shouldn't build on an ancient landslide, because if it's moved once, it's very likely to move again. So these are the two stories that came to my mind as I was thinking about tonight and thinking about geologic hazards. And I gotta be honest, when Dick submitted his proposal, one of the things I'm always aware of is I don't want everyone to come in and have this like doom gloom session of like, the sky is falling and there's no hope and there's the exit. And what I loved about Dick's proposal and what I love about Dick is that it's not about leading with fear, it's about leading with curiosity. And one of the things that I have learned from geologists like Dick is that if you listen and learn a little bit from them, it changes the way you look at everything around you. And all of a sudden, just to drive down the highway, you're noticing, oh, that place I go ride my bike is actually this really cool uplift. Or that spot right by the Bridge of the Gods used to cross the whole darn river. And so it just changes your everyday experience in a way that can teach you something as simple as don't build on an ancient landslide, to teach you something that will crack open this new frontier of, like the architects and engineers in Japan did. And to me, that's very hopeful. So despite the scariness that this topic can have, I think there's also a lot of hope and a reminder that human agency plays a role in all of this as well at times. So, in talking with Dick before the show, a couple of the things that he said to me that we're going to hear more about tonight was this area is one of the most active geologic places in this country. Alaska obviously has a lot going on, Hawaii does, but we're really, when it comes to geologic activity, in a really amazing spot. And you're going to hear more about why tonight. The other thing I loved, and anytime I'm talking with someone who's a real expert, I love when they just get going and don't realize they're talking to me. The excitement he had telling me how youthful. The youthfulness of the geology here is amazing. And so, just millions of years instead of many hundreds of millions of years. So, I love that. And Dick, some of you guys may have seen him. He presented a few years ago with us during COVID time, so I'm very excited to have him here in person. He spent 34 years at the U.S. Geological Survey's Cascades Volcano Observatory. And he still is a scientist emeritus with them. His focus at the time was on the dynamics of debris flows, landslides, and volcanic eruptions. And in particular, he was studying those, but looking at sort of the downstream hazards and how you evaluate what happens downstream from those Cascade Mountains. And I'm imagining most of us live downstream here in the Gorge, and so he's a really good person to hear from. So please help me in welcoming Dick Iverson to Sense of Place Season 15.
Well, thanks a lot, Sarah. It's certainly a pleasure to speak here. Those of us who live in or near the Columbia River Gorge are very lucky to live in a place of exceptional natural beauty. But as Sarah just alluded to, a lot of that beauty actually stems from the geological youth and activity of the area, our mountains, our deep gorge, and so forth. It's all due to a very active geologic setting. However, that activity comes along with some hazards. I don't think of the geologic hazards in the gorge as being severe, but I do think of them as being significant enough that we need to pay attention to them, and in some cases maybe take action in response to what we recognize about those hazards. So this is not intended to be a talk on general geology, but I thought I'd be remiss to not start out with a kind of the broad geologic picture that really is responsible for the hazardous processes that exist around here. So I'm sure that most of you are aware of the concept of plate tectonics and the fact that we live on what's called a convergent margin of two tectonic plates. We live here on the North American plate. Offshore, about 100 miles, is the Juan de Fuca oceanic plate. And these two plates are converging towards each other at a rate of several centimeters a year. And as a consequence of that convergence, there's this feature known as the Cascadia Trench. And that's where the oceanic crust of the Juan de Fuca plate is being subducted underneath the continental crust in this subduction zone. And it's the presence of this subduction zone and the convergence of these two plates that gives rise to our mountains, it gives rise to the magma that produces our volcanoes, and of course it gives rise to the potential for great subduction zone earthquakes. So my talk is going to focus on these three kinds of hazards, or at least I've broken them into three broad categories that range from those that are limited in their geographic extent, that being landslides and debris flows, to those that are a little bit more expansive in their geographic extent, volcanic activity, and then finally with hazards that are broadly regional in their extent, those being earthquakes. I wanted to say a few words about the conceptual basis of geological hazard assessment. So in the hazard business, we tend not to pay a lot of attention to the broad sweep of geologic time, hundreds of millions of years and so forth, because what's really most important is that with a recent geologic past, and to a geologist, recent means about 10,000 years. So why do I choose 10,000? It's a somewhat arbitrary figure, but there's actually a pretty good reason for that. And that's that there's really no need to concern ourselves with the kinds of hazards that existed around here, say, more than 12,000 years ago, going back into the Pleistocene time, or sometimes known as the Ice Ages, because, of course, that was the time of the Missoula floods that rushed through the gorge. Where we're situated right now, the water would have been as much as 500 feet deep over our heads here. So those were truly cataclysmic events that happened repetitively as a result of the breakage of a glacial dam that was impounding a big lake. And that simply won't happen anytime in the foreseeable future. And maybe it won't happen for millions of years into the future. We can't say for sure. But we need not concern ourselves with those more ancient geologic events when it comes to hazard assessment. I wanted to mention the important role that LIDAR technology has played over the last few decades in helping us identify hazardous geological events of the recent past based on their topographic signature. LIDAR is an acronym. It stands for Light Detection and Ranging. And it's pretty complicated in detail, but it's reasonable to think of it as just a type of laser scanning that's not so entirely different from laser scanning that you might use to scan a barcode in a supermarket. This is done with aircraft, shooting pulsed laser beams down at the Earth's surface. And what it yields is very, very detailed picture of the topography, much more detailed than we ever had access to in the past. A typical horizontal resolution is about 1 meter. Typical vertical resolution is about 10 centimeters. So it's a very detailed picture that provides all sorts of clues that we really weren't aware of in many cases until the 1990s when this technology started to emerge. At least it's an airborne technology. I'm also going to be mentioning some dates of recent geologic events, and so I wanted to say just a few things about dating techniques. Of course, for the recent past, we can rely on historical records. Those are the most conclusive records of all. Extending farther back into the past, we can use tree ring dating, which is also called dendrochronology. And this involves a lot more than just simply counting tree rings. We're all familiar with that process of counting tree rings. It also involves a lot of statistical techniques using cross-correlation, that sort of thing, to compare sequences of tree rings from one tree to another, including both living trees and dead trees. And here in the Northwest, that tree ring dating has been pushed back beyond 1,000 years into the past at this point. And so that provides a very high resolution way of dating events in many cases during the past 1,000 years. Then going farther back in time, we can use radiocarbon dating of buried organic material, typically wood or charcoal. And radiocarbon dating goes back to about 55,000 years. And so that takes us well back into a time that's more than sufficient for geologic hazard assessment. There are these other kinds of dating techniques as well, tephrochronology, paleomagnetism, and so on. But those are more specific to certain circumstances. I'm also going to briefly mention the role of models in hazard assessment, both statistical models and also physically based models, where we try to simulate the actual physics of the processes using mathematics and computation. So now on to the first of my technical subjects, which is landslides and debris flows. These are two situations that many of you are doubtlessly familiar with. One here is a landslide that occurred at the eastern margin of Bingen back in 2009. You can see here where I'm pointing with the cursor, you can see the headscarp of this landslide. Here's the body of the slide. And the real issue here from a hazard standpoint is that this was spalling rocks off down the slope and actually threatening inhabited areas here at the foot of the slope, and it led to some evacuations at that time. This landslide was probably partially triggered by quarrying activity that had been going on for some time at the foot of the slope and sort of gradually destabilizing it. But it was also, another contributing factor was the fact that this happened in midwinter during a very wet period. On the right here is a photograph of a debris flow that became quite famous because this was the situation that you could see right along I-84 for several years after this happened. This occurred in 1996, and it was one of many debris flows that occurred in the area here at that time. And immediately adjacent to this site, unfortunately, there was a fatal debris flow that occurred in this same Dodson area. And I'm going to be talking about this in more detail later, so I'll now move on. I did want to, Sarah mentioned this term hummocky topography. So this is the term that geologists use to describe lumpy, irregular, sort of deranged topography associated with landslide activity. And the way this hummocky topography develops is illustrated by this landslide that was very fresh when I first saw it, that took out Piper Road adjacent to Rock Creek and Stevenson, and ultimately did end up destroying 2 homes that were built here as well. But what I want to point out here is this very rugged topography that's been created by the landslide activity here at its headscarp, and here's a big block of material that's downdropped, and then here's one that's thrust up a little bit relative to that. What happens over time is that this very rugged characterization of the landslide topography starts to fade, and it becomes more muted as a result of erosion and so forth. But what's left behind is sort of a muted version of what you see here, lumps and bulges and depressions and so forth that are sort of unnatural in most topographic settings and are oftentimes indicative of ancient landslide activity. Turning to debris flows, they're really better characterized by looking at a video clip than they are with a still photograph. And so if you could go ahead and play the video now. This apparently needs to be played separately in order to get the sound to come through the system. So this debris flow occurred downstream from Semeru volcano in Indonesia in 2002. And this is some especially good footage of a debris flow. It can also be termed as a lahar simply because it originated on a volcano. This was rainfall triggered, not triggered by volcanic activity. And you can see that as the flow is at a distance, it looks more or less like a flash flood of simply muddy water. But as the flow front draws closer, you'll be able to see that this is chock full of large boulders. And it's moving fast. It's moving at a rate of roughly 10 meters a second, which is 25 to 30 miles an hour. I think if I had been the videographer here, I would have been a bit more cautious about pulling back sooner, but they did manage to get some great footage, this group of French researchers. So anyway, that's what a debris flow is. And not many people get an opportunity to see those in real time, and so videos make a good way of illustrating that. So I now want to move on to some map depictions of landslides here in the central gorge, focusing first on the Oregon side of the gorge. This is a piece of a map created by Dogami, the Oregon Department of Geology and Mineral Industries. And this is based mainly on interpretation of LiDAR data with some spot field checking. I want to point out just a few things here. One is that there's a large area of deep-seated slope instability in and around Cascade locks, quite a broad swath of terrain here. There are smaller areas of deep-seated landslide instability closer to Hood River. This is in the vicinity of Mitchell Point over here to the west of Hood River. And to the east of Hood River, these deep-seated landslides are immediately adjacent to and in some sense overlapping with the path of the scenic highway trail that runs between Hood River and Mosier. These things are oftentimes hard to recognize when the terrain is heavily forested. But if you get out and walk around in this terrain, as I have done in these locations, you can see lots of evidence of this kind of deranged topography, the hummocky topography that's characteristic of landslide terrain. None of these have been active in recent times, but as Sarah mentioned, where there is an old landslide present, assuming that it isn't now completely flat ground, there's always the potential for it to become reactivated. I also wanted to mention this Dodson debris fan here. This is an area just a little ways west of Cascade Locks that has been subject to recurrent debris flows, and I'll talk about that in some detail. So now turning to the Washington side of the gorge, this is another map, in this case created by the Washington Department of Natural Resources Geologic Survey. And you can see it looks different from the Oregon side map, and that's simply because the two agencies have slightly different ways of doing things, but the basic information content here is much the same as for the Oregon side. And I want to focus particularly on the abundance of these large, deep-seated landslides here on the Washington side of the gorge, particularly in and around Stevenson, and especially the famous Bonneville landslide here that at one point dammed the Columbia River. Also notice that there's an old deep-seated landslide just east of Bingen that encompasses a good chunk of Burdoyne Mountain here. And an interesting aspect of that particular landslide is that the Coyote Wall, which I'm sure most of you are familiar with, it's so prominent when you're driving east on Highway 14 from Bingen, is actually the lateral margin of this big old landslide. So you know how large the Coyote Wall is. This is quite a substantial cliff. And think of how much material had to be evacuated by this landslide in order to leave that as its lateral margin. And of course, that material probably wound up in the Columbia River and was carried away long ago. So this again is an area that hasn't shown recent signs of landslide activity, but it was obviously very substantial in the past. So I want to say a few things in detail about the Bonneville landslide and adjacent areas. The Bonneville landslide is interesting for several reasons, not least of which is that it did dam the Columbia River. Its date of occurrence is known quite well, roughly around the year 1440. And in fact, the dendrochronologists tell me that now they believe they can actually identify the exact 1 or 2 years during which this landslide occurred, probably 1447 or 1448. And when it dammed the river, it created a landslide dam roughly 75 meters high, and that resulted in backing up a lake upstream along the Columbia River that went all the way up into eastern Washington, all the way to Wallula Gap. And that lake depth can be estimated because we know the landslide thickness in this area was about 75 meters. And so the time for that lake to fill, based on that thickness and based on the volume of water, how much river flow would be required to fill that lake with that volume of water, the best guess is that this landslide dam lasted for about 1 month before it was breached. And the river started to flow again through this area. But nonetheless, that was a big deal, obviously, to the Native American population at the time, and hence the Bridge of the Gods legend persisted. I also will mention that this Bonneville landslide here, you'll notice this is a great representation of this hummocky, lumpy topography, and a lot of the depressions in that topography are filled with small ponds and lakes and so forth. That's very typical. This, by the way, was a very large landslide. It was about 1 billion cubic meters of material. That's 1 cubic kilometer of material. And you can see adjacent to it here, there are these other areas of landslide activity. All this brown shaded area is landslide area. And some of this is still active today, is still moving today. And in fact, this particular landslide here, called the Crescent Lake landslide, has been studied fairly extensively during the past decade or so. And it's known that large parts of this are still moving at rates of about 10 to 30 centimeters a year in response to seasonal rainfall. And also I'll mention that the town of Stevenson is known to be built almost entirely on an old landslide. And of course, the part of that was reactivated in 2007 is shown here as this quite small-looking Piper Road landslide that I showed you the photo of earlier, that nonetheless destroyed 2 homes. So questions that often come up about these big, deep-seated landslides are what caused them in the first place, and also how rapidly did they move. So we can't really say what caused any ancient landslide. We simply don't have the data to reach firm conclusions. But one thing I will say in passing is that there's often a tendency for people to want to attribute these kinds of landslides to some very specific trigger, for example, an earthquake trigger. But the reality is that the great majority of landslides are not triggered by something as conspicuous as an earthquake. They're simply due to the accumulation of water pressure underground due to rainfall patterns. And when things have been particularly wet, that's when landslides are more prone to moving, simply because the water pressure underground is pushing against the soil particles or rock particles, and thereby reducing the frictional contact forces between those particles, and that's what enables the material to slip and slide. So an example of a serious landslide that was triggered exclusively by rainfall was this Oso landslide that occurred in Washington, northern Washington, back in 2014. This is very noteworthy because it was the deadliest landslide in US history. And I've spent a lot of time studying this landslide, and we know a lot about how fast it moved. It reached speeds of about 60 miles per hour at its peak as it was crossing the floodplain here. And the question is that the way the Bonneville landslide acted? Or could other deep-seated landslides within the gorge move so rapidly and therefore be so devastating? Again, that can't be answered with certainty, but my best guess is no, they would not behave that way. And the reason basically just has to do with the differing geological materials involved. So here in the case of Oso, this whole thickness of material that was involved, which was a couple hundred feet thick, was loosely consolidated material that in some sense was of glacial origin. It was either glacial till deposited directly by glaciers, it was proglacial stream sediment deposited by streams draining the front of glaciers, or it was sediment deposited in a lake bed, what we call a proglacial lake, in front of a glacier. And those kinds of young, loosely consolidated materials can be very prone to liquefaction when they start to move. And that's exactly what happened here at Oso, is that the friction went almost to zero as a result of liquefaction as it started to move rapidly. And that's why it ran so fast and so far. Whereas the landslides in the gorge are composed largely of rock. The most prominent rock of all being the Columbia River basalts, the big high basalt cliffs that you hear and see in many places around the gorge. There are other materials involved as well, but just the absence of this really thick sequence of loosely consolidated material in the gorge makes it much less prone to that kind of high-speed, really lethal kind of motion. So now turning to the Dodson area, which is somewhat of a unique location within the gorge, particularly in terms of debris flow hazard. So back in 1996, those of you who lived here at the time recall that we had this massive storm in early February of 1996. It was a sequence of atmospheric river-type storms that were bringing very heavy rainfall, warm rainfall. And to make matters worse, that had been preceded by a substantial low-elevation snowpack. There were several feet of snow on the ground at elevations of, say, 1,000 feet when that storm cycle began. And that combination of things caused a great deal of runoff, really drove up the water pressure within the soil and the rock in the area, triggered landslides that then evolved into debris flows. And the most famous of those was this one that came down a small drainage called Levens Creek. It's sometimes referred to as the Royce debris flow because the elderly couple who lived in this house were named the Royces. And I had the opportunity to talk to them just a couple days after the event occurred. We were allowed, the freeway was closed. I-84 was closed for about a week, but as scientists with the USGS, we were allowed to come in and start investigating this. Got the opportunity to talk to the Royces, and it was really interesting because they had quite a harrowing tale of how they escaped with their lives and not a lot else. But to me, one of the most interesting parts of the conversation was that we'd been talking for probably about an hour, and just sort of offhand they said, well, you know, when the old house was hit, and so, you know, to a geologist, it's like suddenly your ears perk up, and it turned out that this property had been in their family for roughly a century, and they had a house that was destroyed here previously, back around 1920, by a debris flow. And so that was clear evidence this is a recurrent problem in this area. And a particularly sad example of that recurrence was this fatal debris flow that occurred in the drainage immediately adjacent, the Butcher Creek drainage, back in January of 2021. This again was due to an atmospheric river-type storm, not quite as potent as this one in 1996, which was regional in scale. It affected the whole Pacific Northwest and caused flooding in places like the Columbia River and the Willamette River. This was more localized, but nonetheless, there was a woman who was awfully unfortunate with her timing because she was driving along this frontage road at precisely the time this flow issued from this canyon, and it completely buried her car, and that was not a survivable circumstance. So what makes this area around Dodson so prone to debris flows in such a high hazard area? Well, it's a combination of things. One is just the sheer amount of relief here. Nesmith Point at the crest of this area is nearly 4,000 feet in elevation. And here at the apex of this debris fan, the elevation is about 1,000 feet. So there's nearly 3,000 feet of elevation change between here and here, which is a distance of only about 7/10 of a mile. So it's really steep terrain. I think the steepest area of this extent anywhere within the gorge. On top of that, there's some really rotten rock up in the upper part of these head walls. And that's associated with volcanism that occurred here more than 1 million years ago that produced some rubbly volcanic deposits, some kind of cindery type deposits. Some of it might also be something called hyaloclastite, which means it was erupted underwater, and that always makes for very loose, rubbly types of volcanic deposits. And so there's weak rock forming the head wall here, sitting on top of harder rock of the Columbia River basalts. And then to make matters even worse, this is the section of the gorge that probably gets the heaviest annual rainfall. You know, particularly up here at an elevation like Nesmith Point, it probably gets, this is just an estimate on my part, but I'm estimating about 100 inches a year on average of rainfall. Whereas, for example, here in Hood River, we get about 30 inches a year. So this is really wet, it's really steep, and it's weak, and that produces these recurrent debris flows. And what we learned when we were investigating this back in 1996, we had the opportunity to walk across much of this fan, and essentially this entire fan is composed of old debris flow deposits. So that's a good indication that it's going to be prone to debris flows again in the future. So now moving on to volcanic activity. A point I want to make just in passing is that the modern edifices we see of our two big volcanoes, Mount Adams and Mount Hood, are roughly 500,000 years old. So the volcanoes themselves, as we see them today, are really quite recent, geologically speaking. However, both of these volcanoes sit on a platform of older volcanic rocks that dates back as far as 40 million years. And so there is an older sort of ancestral version of the Cascade volcano range that probably looked very different from our current volcano range today. And the modern big stratovolcanoes that we see are just sort of perched on top of that very large volume of older volcanic rock. So one key thing to know about regarding Mount Adams and Mount Hood is that among all the Cascade volcanoes, they've actually been two of the least active in terms of recent eruptive activity. This graphic shows a span of 4,000 years before present. up and down the Cascade Range here, or at least the United States part of the range. And you can see that over the span of 4,000 years, in the case of Mount Hood, there have been two significant eruptive periods. One was in the late 1700s, but it was actually quite minor when viewed in the larger context. It did shed some debris down into the Sandy River and actually resulted in the naming of the Sandy River by Lewis and Clark when they descended the Columbia in the early 1800s. And they named it, as I recall, the Big Sand River because there was so much sediment being disgorged into the Columbia River down the Sandy. A larger eruption of Mount Hood occurred about 1,500 years ago. That's known as the Timberline eruptive period. And that did involve some debris avalanche activity, some large lahars. It was substantial, but it all was concentrated on the south side of Mount Hood. Mount Adams has been even less active in recent time. Both of these were largely lava flow type eruptions on Mount Adams. And there was a little bit of very minor explosive activity associated with that, but the deposits from that explosive activity are all restricted to being right up on the volcanic cone itself. So when you compare our local volcanoes here, for example, to Mount St. Helens, you can see there's a vast difference. Mount St. Helens has been much, much more active in terms of eruptive activity, and many of these eruptions have been highly explosive. So it, in many respects, is a much more dangerous volcano than either Mount Adams or Mount Hood. When we talk about volcano hazards, we like to kind of lump them into a few broad categories, one of which we simply refer to as the proximal hazards, those that apply right up on the slopes of the volcano. And those areas during eruptions are subject to multiple lethal eruption hazards. And I'm really not going to be talking much about those because I'm going to focus more on what happens downstream in areas that are inhabited by significant numbers of people. In those distal areas, more than about 10 miles from the volcano summit, the primary hazards are debris avalanches and lahars, ashfall, which results in deposits that volcanologists refer to as tephra, and dispersed volcanic vents that might pop up almost anywhere. It's also important that particularly with debris avalanches and lahars, these can happen even in the absence of any eruptive activity or any other triggering activity like an earthquake. They can just happen at unexpected times. So the best modern example we have of a debris avalanche that happened without any trigger and transformed into a lahar of substantial size within the Cascade Range was this event that happened at Mount Meager volcano up in British Columbia back in August of 2010. Mount Meager is at the very northern end of the Cascade Range. It's about 100 miles directly north of Vancouver, BC. And what happened is that without any triggering event, about 50 million cubic meters of material failed from the south face of the mountain here, started moving as a debris avalanche, and then transformed into a lahar, meaning more of a liquefied debris flow type event. And it went down this sequence, this sort of sinuous path here of stream valleys, and ultimately discharged across the floodplain of the Lillooet River, completely occupying the floodplain. Did do some significant damage down here, but fortunately this is an uninhabited area, so no one was killed or even injured by the event. There were some people close enough to be quite terrified by it. It happened during the middle of the night, and there were some campers who simply heard the thing coming, and you know, they didn't really know what to think, and luckily they weren't inundated. But this is the sort of thing, of course, if it were to happen at one of our local volcanoes here, either Hood or Adams, this would be a very big deal because it would get down into areas that would have significant impacts on humans. So at Mount Hood, with regard to debris avalanches and lahars, in the past 10,000 years, the big ones have all been on the south side. And that's partly because the modern crater of Mount Hood opens to the south. And this crater was in fact partly formed by a debris avalanche that accompanied the Timberline eruptive period about 1,500 years ago. Also, we're not certain of this, but we strongly believe, based on what evidence we have, that crater rock here, which sort of sits within this horseshoe-shaped crater of Mount Hood, was actually extruded during the Timberline eruptive period. And this is the core of an old lava dome, most of which collapsed and flowed away as pyroclastic flows and that sort of thing. And that's what's responsible for that very smooth southern slope of Mount Hood. For those of you who've hiked up there or climbed the mountain, you know that it's just basically a very kind of progressive, smooth slope. And that's because it's basically surfaced with these deposits from only 1,500 years ago from this Timberline age eruption. This is a hazard map created by the USGS showing hazards from Mount Hood. And the darker colors here on the south indicate the fact that we recognize that the hazard is considerably higher here on the south side of the mountain than on the north side. The last time there was a really big lahar that went down into the Hood River Valley and made it all the way to the Columbia River was 100,000 years ago. So that's not the sort of thing that we think of as being a great hazard today. However, at Mount Hood, we do get these smaller rain-triggered debris flows, which can also be called lahars. And a good example of that were the several that occurred back in November of 2006. This was the biggest of those. This started just downstream from the Elliott Glacier. It started as landslides in the lateral moraines of Elliott Glacier. At the time, some people thought it was due to a glacial outburst flood. That was not the case. When we actually got in there to look at the evidence, it was pretty clear that this started from landslide activity. The landslides mixed with water, liquefied, and then flowed away and left these very prominent deposits. This is along the Lawrence Lake Road crossing. This is farther downstream in the vicinity of the Parkdale Fish Hatchery. And of course, much of the spit, the Hood River spit that's present today, is a result of sediment that came down along with this debris flow and made its way all the way down the Hood River and out into the Columbia. And it's still sitting there today as a reminder of what happened back in 2006. This was an event that was rainfall triggered by an interesting sort of storm. It was an atmospheric river storm, but it dumped most of its rain at high elevations, above about 5,000 feet. And at those elevations, it rained more than a foot over the course of several days. And there was a thin snowpack at that time. At 6,000 feet, there was only about a foot of snow on the ground, and it melted it all. A point that I think is important, particularly as we think about the possible ramifications of climate change in the future, is that if you have much deeper snowpacks present, say a snowpack of 5 to 10 feet in depth or even more than that, the snowpack tends to act as a sponge in that case when there's heavy rain on top of it. And instead of just releasing all the water, a lot of it ends up getting stored within the snowpack and then slowly released. And so it's much less damaging and much less prone to producing debris flows in that instance. And so if climate change brings us thinner and thinner snowpacks on our volcanoes, chances are that that'll result in increased incidence of these debris flow events. So I now want to turn to Mount Adams, and particularly the southwest side of Mount Adams, which you recognize as being a relatively high hazard area because it has such a long history of producing debris avalanches. This is a relatively modest one that occurred back in August of 1997. But nonetheless, it was big enough that it not only covered the avalanche glacier, it overtopped the moraines down here, flowed almost down to the Round the Mountain Trail on Mount Adams, and also produced some small debris flows coming out of some of these distal areas, although none of those proved to be of any real consequence. More importantly than that recent event are two larger events that have occurred in the relatively recent geologic past that originated in this big amphitheater here that's formed by the cirques, the White Salmon Glacier, and the Avalanche Glacier. The head walls of these cirques are sort of exaggerated simply because this is where these big debris avalanches occurred, and so there was a lot of material removed by those and not merely by the glaciers themselves. In passing, I also want to mention that this glacial moraine down here is draped with this debris avalanche deposit that has this sort of yellowish or ochre color to it. That's very characteristic of what we call hydrothermally altered rock. So in a volcano like Mount Adams that hasn't erupted for a long time, there's lots of opportunity for hot hydrothermal fluids, volcanic fluids, to circulate within that volcano. They tend to be acidic, and they actually alter the minerals within the rocks. And the net effect of that is to produce minerals and rocks that are weaker than what they were originally and can also hold more water. And that makes them more prone to producing debris avalanches. And there's a whole lot of that. There's more than a cubic kilometer of that sort of hydrothermally altered rock up around the summit of Mount Adams. Here are a couple of maps. It's actually the same map, just shown at different scales, of deposits from debris avalanche lahars that occurred at Mount Adams within the last 10,000 years. The purple color here is known as the Salt Creek lahar that occurred only about 200 years ago. It was about 15 million cubic meters in volume. It did reach all the way down into the Trout Lake lowlands, but it was preceded by a larger lahar that occurred about 6,000 years ago. This was about 66 million cubic meters of material called the Trout Lake lahar or Trout Lake mudflow. And it not only inundated pretty much all the Trout Lake lowland, but also apparently flowed all the way down to the Columbia River. There are only isolated deposits of it that we found in a few locations here, but the fact that those deposits are present, it makes us strongly suspect it did reach all the way to the Columbia. So that would be a very big deal, of course, if it were to happen today. And as a consequence, the USGS has done some studies trying to prognosticate the behavior of potential future lahars coming off this side of Mount Adams. And so this is based on a statistically based computational model that we gave the name Lahar-Z. This is something we developed back in the 1990s. And basically what it does is it uses the inundation patterns from many lahars worldwide to sort of calculate what the mean behavior is of any given future lahar. And it looks at a spectrum of possible lahar sizes. And certainly small lahars are much more likely to occur than big ones. That's true of many geologic phenomena. That small are more frequent, the big ones are more rare. And in this case, it looks at a spectrum ranging from 1 million cubic meters at the low end to 1 billion cubic meters or cubic kilometers, which is very large lahar indeed, at the large end, and shows how the difference in anticipated inundation patterns vary depending on the size of the lahar. So that's kind of a broad brush technique, and as a result, I've spent a lot of my career developing also a physics-based computational model of debris flow and lahar behavior. And the first place we applied that to is Mount Rainier. I want to show you just a few examples of what we've done at Mount Rainier, simply because this kind of work, using our model that we call DCLAW, is now underway for Mount Adams, specifically for the southwest side of Mount Adams. And so I think it's reasonable to expect that in less than a year from now, we'll have results sort of comparable to these Rainier results available for the southwest side of Mount Adams. In the case of Mount Rainier, the area of greatest concern is the cirque of the Tahoma Glacier here on the western side of Mount Rainier. It's the area that's been identified as least stable on this map here on the left. And so this is a simulation now where we've considered a debris avalanche of 260 million cubic meters. We chose that volume simply because that was the volume of a lahar that did occur at Mount Rainier about 500 years ago, called the electron lahar or electron mudflow. And so here's the way the simulation looks. This is just the first 2 minutes of it. And you can see the material spreads out into several different drainages here, running across different glaciers, and then continues downstream. It reaches very high speeds up here on the mountain, something like 100 miles an hour. And now this is just a snapshot of that same model result, a still action snapshot at time 20 minutes after the onset of motion of the debris avalanche that caused the lahar. And what it shows is that it has kind of bifurcated into several different paths here, a primary path down the Puyallup River and another one down the Nisqually River Valley. And you can also see that within 20 minutes of onset, it's reached the town of Ashford. So that kind of timing information is really important. Many of you are probably familiar with Ashford because it's right along the way on the southwest entrance of Mount Rainier National Park. What's not shown in this illustration, but it's in our report on this, is that this is particularly scary because this is deep when it reaches this point. It's something like 12 meters deep. And so you can imagine a debris flow like that one that I showed the video clip of that's 12 meters deep. That would not be a survivable sort of event. Looking farther downstream, that same lahar moving down the Nisqually Valley ultimately enters Alder Lake Reservoir, which impounds about 100 million cubic meters of water when it's more or less full. And what this shows is that about an hour and a half after the onset of motion, I'll let this play a second time. If you follow the clock here that's scrolling through, when it reaches about an hour and a half, water starts overtopping Alder Dam. And Alder Dam is a 300-foot tall concrete arch dam that was not really designed to withstand an overtopping event. We don't really know exactly what would happen if it's overtopped, but we've certainly made the authorities aware of the fact that there's some potential of this and something to be concerned about. So a couple of additional volcano hazards. One is related to just lava flows and volcanic vents that might pop up almost anywhere around here. There are some big ones in the surroundings of both Mount Adams and Mount Hood. I've drawn arrows here pointing at 3 of them. Some that are best known are the A.G. Aiken lava bed here, which is about 3,000 years old on the south side of Mount Adams. And then there's the Parkdale lava flow here north of Mount Hood, right outside the community of Parkdale. That's about, as I recall, about 6,500 years old. So these sorts of things, these are not the kind of high-speed lava flows that you see video clips of, like Hawaiian lava flows. These are a different kind of lava. It's andesitic rock, which means rock, a type of volcanic rock that has more silica in it, and it makes it more viscous and makes it flow more slowly than a Hawaiian-type basaltic lava flow. So these, if they were to happen today, would probably not move very fast. You could probably outwalk them if you were walking at a fast pace. But nonetheless, obviously, they could be quite damaging if they were to pop up at some unanticipated location, and that's always possible. More broadly speaking, because we do live amid a volcanic mountain range and above a subduction zone, there are really volcanic vents all over the place around here. If you look at a map of all the vents, there are hundreds and hundreds of them on both sides of the Columbia River. And for the most part, these are nothing to be terribly concerned about. Mount Defiance is a volcano, Underwood Mountain is a volcano, but most of these have not been active for many tens of thousands of years, and in most cases more like 1 million years since they've been active. And they also appear to be monogenetic in the sense that they sort of went once, erupted once, and then they shut down and they're done. So nothing to be real concerned about. However, there is always the potential that a new volcanic vent could open up almost anywhere around here. We really have no way of knowing that. So my last point that I want to make about volcano hazards in the area pertains to ashfall. Now, an interesting fact is that a heavy ashfall around here is not as likely to come from Mount Hood or Mount Adams as it is from Mount St. Helens. And that's simply because Mount St. Helens has such a history of producing large explosive eruptions and emitting large amounts of ash and creating big tephra deposits. This is a tephra deposit that I found up along Elder Road, just east of Hood River here. And not much is known about this. I brought in some of my geologist friends who know more about our regional tephras than I do. And our suspicion is that this did come from Mount St. Helens, but the detailed work to really determine that for sure has not been done. I hope it will be done, because I'm mainly just curious about it. It's a fairly substantial tephra layer. So now moving on to earthquakes. I'm showing this photo of damage from the 2011 Tohoku earthquake in Japan, simply because it was a great subduction zone earthquake of magnitude 9, similar to what people anticipate could happen from the Cascadia subduction zone. At this point, we know a lot about Cascadia subduction earthquakes, and that's particularly true given that 40 years ago we knew virtually nothing about these. So a lot of advance has taken place pretty rapidly. We know that the most recent one occurred in the year 1700. We know that exactly based on historical records from Japan of what they referred to as the orphan tsunami. And the origin of that tsunami ultimately was traced back to a source from the Cascadia subduction zone. We know that about 40 of these have occurred in the last 10,000 years, and that about 20 of those 40, about half of them, appear to be big ones, similar to magnitude 9. And those are earthquakes that result from what we call a full rip along the subduction zone, where the whole thing slips at once. It's also possible for just segments of it to go and to produce smaller earthquakes. But the implied average recurrence interval for the really big ones, the magnitude 9 quakes, is about 500 years based on this kind of information. So, on the other hand, kind of a rosier part of this picture is it emerges from this Dogami map of the median shaking severity in northwest Oregon from an ensemble of 30 simulated magnitude 9 Cascadia subduction earthquakes. So this is not data, this is based on model simulations, but it's the best we can do in terms of anticipating the future. And what it shows is that, for example, here in Hood River County, the median shaking severity would not be all that bad. It's ranked here on this Mercalli scale as strong, but with potential damage being light. So not so severe. Now again, that's the median. That's not the worst possible. And I should also mention that this Mercalli intensity scale is probably different from the earthquake magnitude scale you've typically heard of. That magnitude scale is based on sort of the physics of the earthquake and how much energy is released, whereas this Mercalli scale is an attempt to kind of gauge how much actual damage is done by the earthquake and how it affects humans and their structures. A slightly less rosy picture is this one, which is the Dogami map of the highest shaking severity in northwest Oregon that has a 2% chance of occurring sometime within the next 50 years from all potential earthquake sources. So not just the Cascadia subduction zone, but any earthquake fault that might affect an area. And you can see here again that in Hood River County, and this would also apply in adjacent areas in Washington State, the shaking severity now is ranked from very strong to severe, damage from moderate to heavy. So that looks a little more consequential. And the fact that that considers earthquake activity other than just from the Cascadia subduction zone, I think is good reason to think about our local faults around here and what is the earthquake potential of faults that are very nearby. And I want to focus on some recent findings from a fault segment here that's part of the Mount Hood fault zone that runs more or less right through Mount Hood in the north-south direction, comes out here to the Columbia River and actually crosses over into Washington, although it's not shown here. And it's one of many faults and fault segments here around the Hood River Valley, which is bounded on both sides by fault zones. The Hood River Valley is what we call a graben, which means a block that's sitting down relative to uplifted blocks on either side, uplifted along faults. And so it is an area that has a history of faulting and earthquakes. So this Gate Creek fault segment of the Hood River fault zone, and to get your bearings here a bit, here's Mount Defiance right here. And this is the same map. Here's Mount Defiance again, but with some extra stuff drawn in. And what was interesting is that this really wasn't, nobody really knew about this until the advent of LIDAR and people started looking at this highly detailed topographic data. And the geologists from Dogami who first did that recognized that there was this linear trend along here. You can see if you follow my cursor, there's a whole bunch of things that just sort of line up linearly. And geologists appropriately enough refer to that as a lineament. And whenever they see a lineament, they suspect that there's something like a fault or some other structural reason for that. And indeed, there is a fault segment that runs right through here. And I'm going to show you a couple images of details observed along that fault segment. So here's what it looks like in the field in one of the more conspicuous areas. There are two people standing here for scale. They're a little hard to see in the shade here in the shadows, but you can see there's a significant fault scarp here. And this is a profile, a vertical profile across a trench that was excavated across this fault scarp. And this was done, it was a very laborious operation because the trench was dug by hand. Since this is in a wilderness area, they could not use power equipment. And it was a consortium of people involving the USGS, Dogami, and some local university folks. And they succeeded in digging this trench and creating this sort of profile, which shows this very clear offset, particularly if you look at this gray material here that's referred to as lodgement till. That's a type of glacial till that's deposited right at the bed of a glacier, so it's very compact. that it's offset by more than a meter vertically. And they've dated these materials using radiocarbon dating and have found that this offset dates to the early 1400s, so it's not all that long ago. And an offset of this magnitude along the length of that Gate Creek fault segment would produce an earthquake of roughly magnitude 6. So that's pretty big, considering how nearby it is. Furthermore, if nearby fault segments ruptured at the same time, it could produce a magnitude as large as 7. However, I do want to make the point, and this is something I think isn't widely known outside the earth science community, is that the earthquake magnitude scale, the so-called moment magnitude scale, is not a simple linear scale. It's actually a logarithmic scale. And not only is it logarithmic, but it doesn't use a common base 10 logarithm. It's a base 32 logarithm for sort of arcane physical reasons. And what that means is that a magnitude 9 earthquake, as from the Cascades subduction zone, releases 1,000 times more energy than a magnitude 7 earthquake. So that's huge. That's a huge difference in energy release. Just the same, a magnitude 7 would be a pretty shaky event around here were it to occur so nearby. And that's why I want to mention something that's available to anybody who has a smartphone. And that's something called the Shake Alert system, which is something developed by the USGS in consortium with some university folks. And what this is a way of issuing early warnings of impending earthquake shaking. And by early, I don't mean days or weeks in advance. I mean a few seconds in advance, or perhaps as much as 10 or 20 seconds in advance in the best circumstance. Well, you think about that could be very consequential depending on where you are and what you're doing. The picture I always imagine for myself is, suppose I'm just about ready to drive out onto the Hood River Bridge, and I get this shake alert. And the one place around here I don't want to be during a big earthquake is out in the middle of that bridge. So this would give you time to put on the brakes and simply stop. And the way this works is kind of interesting. It's all based on what's known about the physics of the travel of seismic waves, and the fact that the first arriving seismic waves are known as compressional waves or P waves, and they move about twice as fast as these later arriving surface waves that do most of the damage. The surface waves are the ones that give rise to the actual sort of rolling motion of the Earth's surface that looks almost like water waves on the ocean. And what that means is that if you're at some distance from the earthquake source, with modern technology nowadays, with dense networks of automatic seismometers that transmit their data back to a central computer that can then process that data very rapidly, make rough estimates of where the earthquake originated and where the seismic energy is heading, that's what enables them to actually, through the cellular phone network, to put out warnings some time in advance. And that's particularly critical for really crucial facilities. The other scenario I imagine is, suppose that you're in the hospital in the middle of an operation. You'd really like the hospital to be able to shift over to their backup power, before all the power goes out in the middle of your surgery. And this offers the potential of doing this. So this is something you can sign up for. You can implement this on your smartphone pretty easily. I know in the case of my iPhone, it was quite easy to do. I think it's slightly more complicated on an Android phone, but not that much more complicated. And I think it's worth doing. You just have to try Googling Shake Alert, and you'll find lots of information about this. It's all up and down the West Coast: Washington, Oregon, California. So I've covered a lot of ground in a hurry here. There are lots of sources of further information if you're curious. I'm not going to go through all these in detail, but these are all agencies and organizations that have excellent websites with a lot of additional information about geologic hazards in the area. So I want to conclude by making this point that on balance, I feel like, sure, there are geologic hazards around here, but on balance, I feel like the benefits of living here, the scenery, the inspiration you can derive from the natural setting, all the recreational opportunities and so forth. I feel like it's well worth living here. And in fact, I actually feel safer from a geologic hazard standpoint living here than I would if I were living in a big city like Portland or Seattle. And the reason for that is that those big cities have so much infrastructure, so many important bridges. You know, there's so many things that can go wrong just due to the sheer volume of stuff that could be affected. Plus, they're a lot closer to the Cascadia subduction zone than we are here. So, although there are hazards, I don't I don't recommend that anybody move away just because of that. So thank you for your attention.
All right. God, I don't know who that obnoxious person in the corner with a tickler in his throat was, but woo, rude. Joe, if you'll bring up the lights a little bit, this is your chance to ask your questions and get answers. Let's go to you.
Could you say a little bit about the recent little earthquakes that were at Mount Adams?
Sure. Those I've talked to the seismologist who's been most engaged in looking at those data, and basically he says, well, we don't know much at this point other than that they're very small earthquakes. It's been very difficult to get exact locations on them because they are so small. The USGS did deploy 3 temporary seismometers around Mount Adams in addition to the 1 permanent station that's nearby on Crofton Ridge. But at this point, they just don't have enough information from enough sizable earthquakes to say anything definitive other than that they're happening somewhere on or you know, right around Mount Adams, and they're not big enough to really be of any concern.
All right.
Hi. With the increase in fires in the area, both large and in intensity, how do fires in like landslide areas impact the probability of a landslide? Like the microwave tower fire just burned in the entire area of that landslide.
Yeah, that's a good question. You know, fire impacts probably don't have much influence on the big, deep-seated landslides. But in terms of things that originate as shallow landslides, meaning debris flows specifically, it can have a substantial impact. That said, and in some parts of the country, that's a very big deal. For example, in Southern California, which is a very different geologic and climatological setting than we have here, they have a severe problem with post-wildfire debris flows. Here, because our soils are different, our vegetation is different and so forth, it doesn't seem to be quite as much of a problem. And following the Eagle Creek fire in 2017, some people were predicting widespread debris flow problems impacting I-84 and so forth. That really hasn't played out. There was the one fatal debris flow in 2021. And there have been, you know, some other smaller debris flows in the Eagle Creek burn area, but nothing like the sort of devastation they've experienced in Southern California, for example.
All right. Oh. Okay. Yeah, don't be shy. Let's get as many as we can.
So when subduction happens, how bad, I mean, is shell rock just coming down on the freeway? How isolated are we going to be?
I can't answer that question other than that, you know, as I showed you with that one map, the shaking severity here will not be what it is west of the Cascades, and certainly not what it will be along the coasts of Oregon and Washington. However, because there are so many cliffy areas right along the gorge, bordering the highways on both sides of the river, chances are there are going to be rockfall events, which will result in some blockage of the highways, and it'll take some climb to clear that. And of course, there's going to be a lot of chaos in general following that. It's that sort of widespread societal impact, and particularly in the big cities of Portland and Seattle, which of course we're so connected to around here in terms of the way commerce flows and so forth. So it's going to be a major disruptive event for sure, but I would expect that here, you know, kind of a little ways east of the axis of the Cascades, there isn't going to be the kind of really devastating impacts that there will be in some other parts of the Northwest.
Okay, so I have a question. You mentioned the Hood River Bridge, which we all love. And we all recently found out that the new bridge is going to cost almost twice as much because everybody had assumed that the current bridge had the pilings were anchored into bedrock, but it turns out that they're not. They're on top of gravel. And so I was just curious. Yeah, I also laughed when I heard that. So I was just curious, as a geologist, how you're thinking about the current bridge might have changed, learning that it is not anchored into bedrock, it's anchored into gravel, or if that changed anything at all.
Well, I have to say, when I read that story in the Gorge News, I was a little bit surprised at the engineers and others who've been engaged in this project already hadn't thought about that issue sooner. Because certainly if you want the bridge to be earthquake resilient, you do want the piers to be anchored in bedrock. And I guess I'm not sure why it hadn't occurred to anybody to think about that at an earlier stage of the process.
All right.
Now, I have kind of a silly question, but did the Royce family rebuild again?
So there was an adjacent farmhouse just a little ways to the east of the one that was destroyed, and I think, they had sort of a multi-generational living situation there, and I'm pretty sure that the elderly Royce couple, at least temporarily, moved into that adjacent house. However, the house that was completely surrounded and filled by the debris flow, that was abandoned, and then we quit seeing it after about 6 or 8 years because the vegetation grew up around it, so it wasn't so conspicuous. But then along came the Eagle Creek fire in 2017, and that burned the house down. So what was left of it is no longer left of it.
That's a bad place to put a house.
So I have a question that's a little bit different, and that is, how dangerous is it to be driving near these big cliffs, especially during heavy rain or ice, that kind of stuff? I always feel like I want to get past them really quickly because
Yeah.
I feel like big rocks could be coming down.
Well, you've probably noticed that along I-84, both east and west of that Dodson area, there are now signs that were put up by ODOT following the 1996 event. And it says hazard landslide area or something like that. And there are times when they have actually closed that section of the freeway preemptively because it's been raining really hard, and they think, now's the time it's likely to happen. And so I think that's actually a good thing. It's obviously an inconvenience, but I think the preemptive closure is a good idea. Yeah, some of the vertical, those steep, cliffs that are made up of the basalt cliffs, the Columbia River basalt, there certainly could be chunks of rock that topple. Those are probably less influenced by what's going on with the weather at any given moment than just, you might get really unlucky. You happen to be driving by when a big chunk of rock falls off. I don't know what else to say.
Can we call you?
Yeah.
Let's get one more question, and while you're thinking of your good question, I'm going to cut in line and do another question, which is, can you remind me, someone explained to me once why the Oregon side is really steep cliffs and the Washington side is more gradual?
Sure. So a lot of that has to do with the regional dip of the rocks, and particularly if you think of the Columbia River basalt, the big cliff-forming basalts. For example, that photo I showed you of forgetting the name of it now, the cliff east of Bingen. Yeah, Coyote Wall. That, you could see how that dipped down towards the river. Now there the dip is greater than it is in some places, but in general, throughout the gorge, the rocks, those older rocks, do tend to dip down towards the south, and that kind of creates a nice, surface that's predisposed to slotting because the rocks are already kind of headed in that direction down towards the river. Whereas on the Oregon side, that same dip, is going into the cliffs, and so that's why erosion on the Oregon side tends to form these steep cliffs rather than these big landslides.
Okay, now we know. Okay, one more question. No pressure. And then Dick will probably stick around. You can ask more after. That's okay. You got tickle throat too.
I do. Okay. I really want to know the difference between an anticline and a syncline. I do not. I've been told many times, and I don't get it.
Yeah, so an anticline is just rock that's folded up. So if you imagine rocks that's originally horizontal and now it gets folded up like that, that's an anticline. Whereas if it gets folded down like that, it's a syncline. And the thing that people refer to around here as the syncline, which is kind of over around the Coyote Wall there, is actually pretty hard to see. I think that the best way you can see it is to be on the Washington side, like someplace around Catherine Creek, where you can look across over at Mosier, and from there you can see that sort of the axis of the syncline kind of goes right through the community of Mosier. But it's fairly subtle. It's not a really dramatic syncline.
You feel good about that? Yeah. Okay. Okay. All right. You know my last question. I'm going to give you one question, and then while you think about it, I'm going to do some updates to them. Joe, if you'll pull up my slides. Okay. If you were a geologic hazard, what would you be and why? Okay? Okay.
I would choose a debris flow.
Don't tell me. Don't tell me now. Don't tell me yet. No, I want to be a surprise. Okay, don't tell me yet. I want you to think about it. I told it. Okay. While Dick listens to me and follows my rules and doesn't tell you why. Let's get to my next slide here just to tell you guys about what is coming up next. Nope. That is coming up, but that's not the one I want to show you. Maybe. Joe, are you able to manually pop it back a screen? There we go. Okay. So, coming up, we've got 2 events this month in December. December 5th, this is actually an Oregon humanities event. They're coming to the Gorge to talk to Abigail Elder, who, if you live in Hood River, she's your city manager. Leslie Tamora, if you were here last season, she's a 4th-generation pear orchardist here in the Gorge, and that's me. And Oregon Humanities is a statewide nonprofit, and they do these events largely in Portland, but also around the state, and the events are called Consider This, and they are going to go and dig into a certain topic. And in this case, they're going to come out and talk to us because these 3 women are all involved in one way or another in a project that is going to conclude this season of Sense of Place, which is called the Watershed Rock Opera. You may have seen it in our pre-show slides. Stay tuned. It is as fun and silly as it sounds, and at this event, if you're able to join us, you will learn more of what the opera is, what the hell we're doing, and what's going to happen in April. So that's December 5th. The tickets are being sold through Columbia Center for the Arts, but we also have a link to it on our webpage. So mark your calendar for that. And then we have, Joe, I might need your help again. The Wolf Next Door, Community Perspective on the Return of Wolves. So this was a really interesting one. This is on December 11th. It's our next Sense of Place. Laura reached out. She's a PhD student, and her proposal piqued my interest because she is doing research on human and wildlife interaction, and specifically around wolves. And one of the things that I appreciated was, instead of sitting outside of the gorge doing research and then telling us what to do, she started in the gorge and is starting with a community that's going to be directly impacted by the return of the Big Muddy Pack. And she found out some really interesting things when you go and talk with community members from different walks of life on a topic that can be this contentious and hot. There is still some interesting overlap. And so she's going to talk to us about what she learned in addition to what we know about the return of the wolves. So that's December 11th. So lots coming up. And that is it. Okay, now, and you broke the rules on that too. That's when, Hey, Dick, do you have any final thoughts that you want to share? Yay! You're such a good sport. Okay, tell us what you would be if you were a geologic hazard and why.
So I would be a debris flow,
Okay,
partly because I've spent much of my career studying debris flows.
okay.
But also because I like to ski, and debris flows get to go downhill fast.
I like it. And with that, Geology rocks, and we'll see you in December. Thank you. No, you are a good sport. You're a good